Yeah. Hello everyone. Good evening. So we'll wait for 5 more minutes. Okay. Then we'll start. I'm audible, right? Please confirm.
Yes, sir, you're audible.
Okay. Thank you. Okay. So I think we can start now. Yeah. So first we'll be taking the practice assignment questions. Okay. From week 6. Okay. So how many of you have solved the practice assignment question of week 6? Please raise your hand. Only one people. Okay. Okay. No issue. Okay, so anyone have any problem in normalization form like 1NF, 2NF, 3NF? Any doubt?
Sir,
Okay.
hello, sir.
Hello. Yes. Can you speak louder?
Yes, sir. Am I audible now?
Yes, Abhishek. Yes, yes.
Yeah. So, sir, I am having problem in 4NF. Uh,
Mm-hmm.
that is, if let's say there are uh, uh, PQRST, there are 5 attributes
Hmm.
in a relation, and P is determining. PQ is an MVD, and Q determining ST is also an MVD.
So
So
P multi-determine Q and then
P multi-determine Q, and Q is also multi-determining S and T
yes
together.
and T. Okay.
Yes.
Hmm.
So in this case, by transitivity, we can say that P is also determining S and T, right?
No, no. Transitivity rule is different in the case of multi-order dependency.
Yes, but that is if X determine Y and Y determine Z, then X will determine
Z minus Y.
Z minus Y. So here
Yes.
Z is S and T, and Y is Q. So Z minus that means S and T minus Q will give me S and T itself, right?
Okay.
So P is also multi-determining S and T. We can say that, right?
Wait, let me share my screen.
Yes.
Okay, so let's take relation. Right. Yes, okay. Having PQRS, right?
This is a activity question. So if
Activity
you
question. Okay.
yes,
Uh, yes, question number.
activity 6.4 question number 1.
Okay, just let me check it 1 minute. Okay, yeah, just one minute sharing my screen.
Yes, sir. Yes, sir.
Hmm, question. Okay, tell me. Yeah.
Yes, sir. So here we can say that the P is determining, multi-determining Q, sorry, S and T.
Yes, okay.
Yes, we can say that P is multi-determining Q, S, and T.
Use multi-determining.
Q, S,
Q.
and T.
Uh, how? How we can say that?
P is because P is multi-determining Q, and P is multi-determining S and T.
No, no. Here P is functionally determining Q, na? Not multi-determining Q.
But sir, in my assignment, it is given P. I mean, 2 arrows are given between P and Q.
Yes, sir.
Yeah,
Actually, it's given like that.
the symbols are wrong there. Yes, sir, I agree.
Check. Means it is multi or dependency. P determine multi-determine Q. I check on the portal. Okay, P multi-determine Q and one multi-determine. No, actually it is P functionally determine Q. Okay, you can read the sentence also having only one functional dependency. P functionally determine Q. Yeah,
Okay. Okay.
we'll update that. Okay. Yeah.
Okay, so that is not a problem. So if it was a multi-determine, if P was multi-determining Q, let's for a minute let's consider that.
Okay.
Then can we say that P is multi-determining Q, S, and T?
Okay, Q, then Z minus X will be Z minus Y. Sorry, so Z minus Y will be STQ. So Q ST, yeah. So we can say that from transitivity dependency we cannot conclude that, right? Because Z will be ST, right? Y will be Q. So if we
Yes.
consider that, then it should be P determine R
Yes.
only, right?
P determine ST and P determine Q. So
ST, okay, Z minus Y. Yeah.
if you consider Z as ST and Q as Y, so
Mhm.
we can say that P multi-determine Z minus Y, that is ST minus Q. So there is nothing common, so ST will remain.
Yes, ST will remain, yes.
So I mean, in the functional dependencies, we can combine that P determine Q and P is also determining, let's say, Y. So we can say that P determine Q,
2Y.
Y. Yeah. So in
Yes.
multi-determinacy, can we do that?
Yes, just 1 minute. I'm sharing my screen. It's visible, right?
Yes, sir. Yes, sir.
Yeah. So if P multi-determine Q and P multi-determine say R, then for that we can say B multi-determine QR. Okay. But the reverse is not true always, right?
Okay, we cannot decompose them.
No, we cannot decompose here. Okay.
Okay.
From this, we cannot conclude that P multi-determine Q or R. Okay, it is not valid here. In the case of functional dependency, we can say that, but here it is not valid. Okay, in the case of multi-level dependency.
So in this case, we can say that P multi-determines QST.
P multi-determine, yes, Q, not QST, ST, na?
Yeah,
Wait,
no.
wait. Sorry.
And there is also another multi-determining P.
ST.
I mean, for a second, if we consider that P is multi-determining Q.
P is multi-determining Q and Q multi-determining. And P is also multi-determining ST.
Yes, yes.
Okay. Yes, then we can say that P is multi-determining QST.
QST. And by complement rule, so we can also say that P is multi-determining R.
ST minus ST from here. So P will multi-determining R, right?
Yes. I mean, we have to omit Q also, right?
So P multi-determining R will be there. By by transitivity rule, we can say that, yeah.
Sir, then if there is any multi-value dependency, then it will be a super key, right, sir? Now over here, if you consider P multi-value dependency to Q, then it says that P multi-dependency to rest everything, RST, using complementation.
Okay.
Then we can say P is always super key. No? If you have any one multi-value dependency, then we can say.
For super key, we need functional dependency. Okay. We cannot conclude that P determine RST. Okay. It is multi-value dependency and this is functional dependency.
Then we can't determine any closure for the attribute having multi-value dependency.
No, from multi-value dependency, we cannot conclude. Reverse is not true. Okay. If you see the inferred rule for the MVD, in that you have mentioned, okay, P determine Q we can tell it as P multi-determine Q, but reverse is not true.
Reverse is not true. Yes, sir.
Yeah.
So
Sir, sorry. Actually, my main doubt is that can we find the closure for multi-value dependency using multi-value dependency closure for some attribute?
That will not be correct, right? If we find a for that we need functional dependency only, right? So in practice assessment, we have one question. So we need to decompose that R into 4NF, right? There are multi dependency also and functional dependency also.
Yes, sir.
So let us take that example only. We'll discuss that. Just 1 minute. Sorry. This question was this one, right? It's visible, right? Clear?
yes, sir.
Okay. See here we have given the relation prescription and these are the attribute set. Okay, and these are the functional dependency and these are the multi-value dependency. Okay. Yeah. So we need to what we have to find out decomposition given and identify that one is in 4NF. Okay, so we have to decompose this relation into 4NF, right? So just for my understanding purpose, I will consider this as A, this is B, this is C, this is D, this is E, and this is F. Now from that I can say A determine B, C determine D, and here medicine ID is E determine F, and here A multi determine C. Sorry, multi determine C, and A multi determine E. Right? Is it okay? I'm just considering A, B, C, D, E, F instead of this attribute because it will be easier for us, right?
Yes, sir.
Yeah. So now let us check. Okay, let us check this condition. Okay. So first we need to find out the candidate key. For that purpose, we have to use functional dependency only. Okay. So based on this functional dependency, what will be the candidate key? Yes, anyone? What will be the candidate key based on this functional dependency?
ACE.
A.
A.
ADF, sir.
ACE.
ACE.
Yes, AC, because it is not present on any right hand side of any functional dependency. So this must be a part of candidate key. Okay, so let us take the closure of ACE. From A, we can get B. So, okay, so C is already will be there, ACE. So I am writing it here. From C, we'll get D, and from E, we'll get F. So A, B, C, D, E, F. So we are getting all the attributes present in the relation prescription. So AC is our candidate key. Okay, means A, C, and E are prime attribute, and remaining are non-prime attribute. Okay. Now consider this. Is there any partial dependency in this functional dependency? Is there any partial dependency here? Because A, C, E are the prime attribute, and these are the three partial dependency. Sorry, not functional dependency. Is there any partial dependency here?
Yes, sir. I mean, A is a prime attribute and it is determining a non-prime attribute.
Yeah, so basically all the three are partial dependency. If
All
you
the three are
observe, this is
partial.
A, C, E. And these are the prime attribute and these are the non-prime attribute, right?
Yes, yes, sir.
This relation is not in 2NF.
2NF. So
Yeah,
it cannot be in 4NF.
2NF. So we need to decompose this into 3NF first. So not 3NF, first 2NF. So for that, what we will do? We'll first decompose this relation into 2NF. So yes, I will consider this AR, A, B, C, D, E, and F. Okay, so how to decompose? Based on what condition? Because these three functional dependencies not satisfying our the 2NF condition, means it is having the partial dependency.
So we
Now,
will,
yes, tell me.
so we will have three relation that one will contain AB, one will contain
Okay.
CD, and another will EF.
AB, yes. R2 will be CD
E,
and R3 will be
EF.
EF, right?
Yes, sir.
Is it a lossless decomposition, lossy decomposition? Let us check that thing.
It's a lossy decomposition.
Lossy A, B, C, D, E, F, but there is no common attribute, so we cannot join these three relations and get the original relation, right? So for that we need to add one more relation, and that will be our candidate key, that is ACE.
Yes, sir.
Getting it?
Yes, sir.
So this R, so we decompose this relation R into R1, R2, R3, R4. Okay. Now this, all the four relations are in 2NF, right? Now let us check for 3NF. Now what is the condition for 3NF?
There should be no transitive dependency.
Yeah. So either X should be the super key, or A must be, or right hand side must be a part of candidate key. There should be no transitive dependency. If you observe this R1, so A is the super key for R1, R2, C is the super key for R2, for R3, E is the super key for R3. Means R1, R2, R3 all are in 3NF also, and similarly BCNF also, because this left hand side is a super key, right?
Yes, sir.
And AC is already a candidate key, so it is already in BCNF. So we can say that R1, R2, R3, and R4 are in BCNF, right? Now we'll check for a multi-value dependency here. Now, till BCNF you understood, right? We are not touching a multi-value dependency till BCNF.
Okay, sir.
Now there is multi-value dependency, that is doctor at multi-determined patient, means A multi-determined C.
Yes.
So on which decomposed relation it is applicable? R4, right?
Yes, 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 sir.
Yeah, so we have A multi-determine C and A multi-determine E.
That is not applicable in any.
Yeah, so this R1, R4 is not in 4NF. R1, R2, R3 are in BCNF also and 4NF also, but R4 is not in 4NF because it is having the multi-value dependency. Now we have to remove this multi-value dependency. So for that, we need to decompose this R4 into AC and AE. Okay, so this will be my R5 and this will be R6. Now R1, R2, R3, R5 and R6 are in 4NF. If you observe the correct option, what will be the correct option? This one, right? Last one.
Sir,
Yes.
sir, here, I mean, the condition of 4NF was that MVD should not be trivial, or the left hand side should be a super key, right?
Yes.
Yes. So here A is not a super key, right?
See here A
No, sir. In R4.
in R4. No, R4 is actually candidate key hour. We already determined this ACE as a candidate key. Okay. So is
Yes.
ACE is already in BCNF.
Yes, it is in BCNF, but what I'm saying is we cannot. I mean, I understood why you broke that R4 into R5 and R6. The thing is, what I am asking is RA is not a super key, right? We cannot say that A is a super key.
For R5.
No, sir. For R4.
Yeah, we can't say A is a super key. That's the reason we have decomposed it again.
Yeah.
Yes.
Because this already this is candidate key only. Na A alone cannot determine CE.
Yes.
On this functional dependency, if you, so what are the functional dependencies applicable to R4? A determine, no, not is there. C is also no. Okay, so no, there is no functional dependency, right, which is applicable to R4 based on this parent functional dependency. So A is not a super key here. Combined AC is a super key, but it is having the multi-order dependency also, right? So for 4NF, it must be in BCNF. It should not have any multi-value dependency. And that was the last condition. Which one is super key, right? Left hand side. Yes, Abhishek, you understood, right?
Sir.
Abhishek,
So,
no?
yes, sir. Yes, sir. So in R5, A is multi-value, multi-determining C.
No, R5 and R6 is not MVD here, because for MVD we need at least 3 attributes. So if you observe what is the definition of MVD, if there are 2 attributes which is independent on each other, and the third attribute is determining that 2 attributes, then we can say that it is multi-value dependency. Like A, B, C are the 3 attributes, and B and C are independent on each other, but it is dependent on third attribute, that is A. Then we can say that A multi-determine B or A multi-determine C. For that we need three attributes. Prove that it is in MVD or not. It's following the MVD or not. If there are only 2 attributes, the MVD will not exist there. Okay.
Okay, sir.
So can you tell why R5 is in 4 and
R5.
R5 and R6?
Why we decompose this?
That I understood. Why is R5 and R6 4 enough?
Yes, because it is not having any multi-value dependency, right? So that is the basic condition of 4NF. No? It should not have any multi-value dependency. Multi-value dependency will arrive if there are at least 3 attributes. ACE.
Okay, sir. Okay.
Yeah.
So in R5 and R6, there is no dependency only. No, there is no functional dependency also.
No functional dependency is there. Yeah. So combine AC and AE will be key here. Right?
So how R5 and R6 are in 3NF?
Because this AC in BCNF now already. We are decomposing this, right? And if we apply the what we can say, what is the rule for BCNF here? That left hand side should be a super key, right?
Super key, yeah.
So R5 and R6 will give me a lossless join, right, sir?
R5 and R6 will give you the lossless chain. A is a common attribute.
A is common attribute, but A is not determining any of the relation.
See, actually we're decomposing the candidate key here, right? So it will determine all the attributes. Yes.
But there can be a case that,
AC is a candidate key here for the whole relation.
AC is the candidate key, yes, sir. That is clear. So
and here also AC and AE are the super key, candidate key.
AC and yes, sir. Both will form a super key, and of course there is one super key, so it will be the candidate key and primary key.
Yes.
Yes. So,
Sir, but how A is not a super key, right, sir?
yeah.
From A, can we determine C here? Is there any functional dependency here? From that, we can determine C.
But there is no function dependency between A and C. Then it's not in BC enough, right?
This AC is a combined key here. AC and AE.
So, sir, AC combined form of AC is also not a super key, right?
So functional dependency is not applicable for R5 and R6. Is there any functional dependencies here? No, AC
sir.
and AE are both are the.
Okay, if there is no function dependency, we can conclude that it is in BC enough.
Yes.
Okay.
Okay, sir. Got it.
Wait a minute. Please repeat. If there is no functional dependency.
If now, for example, R5 doesn't have any functional dependency, right, sir?
Yeah, but it should be combined as a key. Okay, all the attribute must be key.
Oh, it should be a composite
Yeah.
key.
If you observe this ACE,
Yeah, it is a candidate key, sir.
Candidate key, yeah, total.
Okay, sir.
So suppose I am giving the relation are A, B, C, and I am not giving any functional dependency to you. So what will be the key here? If I am not giving any functional dependency, just a relation R.
ABC.
ABC, right?
ABC.
Yeah, same concept is applied here. So every table will have at least one super key, and that will be the combination of all the attributes.
Okay, sir.
Okay, sir. Okay, yeah, got it.
Now clear. Yeah.
Yes, sir. I mean, whenever we break a candidate key, we just need to have a common attribute, and that will be a lossless join.
That will be a lossless join. Yeah, but there should not be any functional dependency applicable to that R5.
Yeah.
If it is combined candidate key, means super key AC and AE, then it is already in BCNF. Okay.
Yes, sir.
But you have to see the functional dependency first. Yes, I think there is one more question. This one.
Sir, will 4NF always preserve the dependencies? Sir?
Till 3NF, we guarantee that it will preserve the dependency, but after 3NF, it may preserve or may not preserve. Like BCNF also, it does not guarantee, right?
Yes, sir. Yeah.
Yeah.
We can guarantee only lossless join.
Only lossless join, yeah.
Okay, sir. Yeah.
In 4NF also, we cannot guarantee dependency preservation. Okay, so let's start from question number 1. Yeah. Okay, so relation are atomic values, function dependencies there. Okay, so which is the correct option here? Yes. What is the condition for BCNF?
LHS of all function dependency should be a super key.
Yeah, X must be a super key, right?
Yes, sir. Yes.
Yeah. So if you check the first option, so AB determines CDE. So left hand side is a super key for this relation R, right? So it's satisfying the BCNF condition. So this one is correct option. Now if you go to second option, then A, B, C, D, E. From B we can determine E. So A, B, C, D. So here A, B is a super key, right? But B determine E. Here B is a prime attribute and E is a non-prime attribute. So it has partial dependency, right? So it is not in 2NF.
Yes, sir. Yeah.
Now, if we check for third and option, so A, B, C, D, E. If we take the closure of A, B, we can get C, D, E. So here also A, B is a super key. Now, if we take this condition from C, can we get R? No. From D also we are not getting R. So C determine D and D determine E. So these are the transitive dependencies. So it is not in 3NF. I am taking this relation R and applying this functional dependency. Okay. Not for this particular question. I'm just telling you, okay. The correct answer is option A only. Now, if you observe this, so it is already okay. So AB is the super key here, and same condition applies here. Okay.
Sir,
Okay,
option C is not 3NF because there is transitive property,
transitive
right?
dependency, yes.
Transitive dependency.
Okay, so we'll move on to next question. Yeah, so here we have mentioned include atomic values only, means already in 1NF, right? So R is in 1NF. Now we have to check whether it is in 2NF or not. Yes, anyone?
It is not in 2NF.
Now, what is the condition? First, you need to find out the candidate key, right?
Yes, sir.
So, what is the candidate key here? C, D, E.
A, B,
F,
A, B.
C, D, E, F.
yeah.
All the attributes are present on the right hand side. Then in that case, how to solve this? We will go back to our traditional way. Let us take the closure of each and every attribute, then combination of attribute, and then take that closure. So yeah, it is little much time consuming, but we'll solve that. If you take the closure of A only, B only, C. Okay, from C we can take determine CB, D only, E. Okay, from E we can determine EF. So okay, so alone attributes are not the candidate key. Now let us take the combination of AB. Now AB determines CDE. Okay, AB determines CDE. From E I am getting F. Okay, yes. So AB is the candidate key here, right?
Yes, sir.
Now let us check for AC, AD, AE, AF. For AC, okay, from A, trivial at AC, like from C we'll get B, and from AB we'll get all the relations are, right? Here you can see AB is there, right, in the closure of AC, but from AB we are getting all the attributes. So we can say that if A and B is present, then we'll get all the attributes. So AC is also candidate key, right? Hello.
Yes, sir. AC is also candidate key.
Yeah, because AB is present in the closure of AC and AB is already a candidate key. So AC is a candidate key, okay. Now let us take the closure of AD. Now AD, no, okay, AD only. AE, from E we will get F. Now this is also not AF. So AF, no, only AF. Okay, so AB and AC are the candidate key. Now take for another combination, like for B attribute. B is already taken, so BC. In this way, you have to take BD, BE, BF. Yes, BC is a candidate key or not?
BC gives BC only.
BC, yes, only determine BC, right? Then BD will determine BD only.
BD only.
BE, from
BEF.
F I am getting F,
A.
and from BF I am getting A, and I am getting A and B, so it will be a determine all the attributes. So it is a candidate key. So B is a candidate key. Right, now BF, let us check for BF.
BF also candidate key.
BF, from F we are getting A, so A and B from getting we are R, so this is also candidate key. Okay, so AB, AC, B, BF. Okay, now let us take the combination of C. So C, A and CB we already taken, CD, CE and CF. So CD, no, CE, from E I will get F, and from Z I will get B, right? So B, F is there, from BF I will get A also, means from A and B I will get all the relations, right? So CE is also a candidate key here. Now let us check for CF. So from C I will get B, then B, F, yes, from BF I will get A, and from AB I will get all the relations R. So CE and CF are also a candidate key. Oh, sorry. The CE and CF are candidate key. Okay, now we have already taken the combination of D with each and every attribute. If you observe AD, BD, CD, okay, so we don't need to consider this. Now take the combination of three attributes. Now, if you take the combination of AB, AC, BE, BF, CE, CF with any other attribute, it will give you the relation R because these are the candidate key, right? Is there any other candidate key possible? What is remaining? ADE. So with AD, can I get if I take B? No. If I add B here, so it will be already in. Okay. You cannot add BC here because yes.
No, sir, no candidate key are left, sir.
Yes. Okay. So 1, 2, 3, 4, 5, 6. So these are only the candidate key. Okay. Any question? Any doubt in this? I'm just erasing it. So AB, AC, BE, PF, CE, CF. Okay. Yes, anyone, how to check whether it is in 2NF or not, relation R?
Left hand side should be a prime attribute and right hand side should be a non-prime attribute.
Left hand side should be a
Prime attribute and right hand side should be a non-prime attribute.
Okay. So AB is the candidate key here, so it is applicable. EF, E and F both are the prime attribute. Okay.
Yes.
Now BF itself is a candidate key.
Yes.
Now C is also prime attribute, B is also prime attribute. So it is already in 2NF. Okay. Now let us check for 3NF. From AB, will get all the relations, so it is satisfying. Now EF, whether it will satisfy my third enough condition or not.
No, sir.
Why?
No, sir. Yes, sir. It does. E is a E is a prime attribute. So
Because C is not a super key, no, sir.
that is BCNF, no?
Yeah. So here both are the prime attribute, right?
Yes, sir.
So,
So this
so
is
this
not
is
a
allowed,
transitive
right?
relation. Transitive
This is
dependency.
also allowed, and BF is already a candidate key, and C is also prime attribute, B is also prime attribute. So my relation R is in 3NF also. Now let us
Sir?
check for BCNF.
Sir,
Yes.
one.
I didn't get 3NF.
Okay.
Sir, before that, sir, one thing that AB determines CDE. So C and E is understandable, but AB determining E, that functional dependency, AB is a prime attribute and D is not.
Which one? D.
Yes, sir. AB determining D. So here AB is a prime attribute, but D is not, right?
We have to check in the parent functional dependency. Okay.
Sir, can I add?
Yes, yes, Suvendra.
Yeah, Abhishek. Suppose alpha determine B. So in 3NF, what are the conditions you have to check? Suppose alpha is the super key, then already in 3NF, or
Sir, I am
or
talking
beta
about
is a prime attribute, then it is in 3NF.
no,
Sir,
sir.
can you write alpha determine beta? Sir.
Sir, I am talking about 2NF, sir.
Oh, sorry. Okay. 2NF then. Okay, then there is a partial dependency.
Partial dependency, yes, sir. That is what I am talking about, sir.
Okay.
Partial dependency is whenever there is whenever that prime attribute determining a non-prime attribute, then there is a partial dependency, right?
Yeah, part of a candidate key determine non-prime attribute.
Part of a candidate key, that is proper subset of a candidate key.
Yeah.
Subset of candidate key, yes. It is a proper subset of candidate key or candidate key? AB?
AB. Oh, okay, sir. Okay, sir.
It is not subset, right? It is a proper
Yes,
candidate key. Yeah.
Yes, sir.
Okay. So our relation R is in 2NF also. Yes, someone asked about the 3NF.
Yes, sir, myself.
Yes. Yes, what is your doubt? Yeah.
Sir, actually, if functional dependency satisfies BC enough, then it is in 3NF, right?
If R is in BC enough, then it is in 3NF. Yes.
Then actually the alpha determines beta. Alpha should be a super key now, sir, for 3NF.
For 3NF, there are two conditions. Means alpha should be a super key or beta must be a part of candidate key.
Sir, can we say here, if we calculate the prime attributes, from there only we can tell whether it is in 3NF or not? Because if a non-prime attribute is determining a non-prime attribute, then it is not in 3NF. Otherwise, it is in 3NF.
Yes. Okay, so are you asking this question or what? I'm not getting it. You understood, right? Why it is in 3NF?
Yeah, I got.
Okay. Yeah, for BCNF, left hand side should be a super key. Okay. Now, if you observe this, AB is a super key, BF is a super key, but E and C are not a super key or candidate key. Okay. So this relation R is not in BCNF. So it is in 2NF, 3NF, but not in BCNF. So option B and C are the correct option. Any doubt in this?
Sir, in BCNF part, the if alpha determines beta, then beta should be not in and should be in candidate key, right?
Alpha should be a super key.
Alpha should be a super key and beta.
No, alpha should be super key. That's it. There is only one condition. Or should trivially determine the beta.
Or trivially determine the beta.
In
Okay, means
3NF, there is one additional condition, that is alpha determine beta. This first condition is that this alpha
is a
must be a
super
super key, or A or beta must be a part of a candidate key.
Candidate key. And sir, E determines F in that case. Then if there is no relation between E and F, means E, F is not a candidate key. Therefore, we can say it is not BCNF, right?
Yeah, E is not a super key. If
E
we
is
take the closure of E, are we getting all the attributes? Not.
No.
Yeah, so it is not a super key.
E is not a super key. And also F means I'm saying this, sir, in a specific case like BF. BF is a super key.
Right.
But F is a part of super key.
Yes.
But still it is not get satisfy the condition of BCNF.
No. Right. For BCNF, left hand side should be a super key.
Okay.
Alpha must be a super key. Okay. Is it okay?
Yes, sir.
Okay. If it is a similar question, you can try it. Okay, so what is the highest normal form in this relation R? Yes, anyone? All the attributes are atomic values only. So it is in 1NF. We have to check for 2NF. If it is not in 2NF, then highest normal form will be 1NF. What is the candidate key here? PQ. PQRSTU. VW we are not getting from
PQV.
PQV. Yes, PQVRSTU WW. Yes, from V we'll get W. Yes, so PQV is the super key here, and PQ and V are the prime attribute. Right?
In PQ we are getting RSTU, right? So from R you are getting UV.
From R you are getting UV, right?
So PQ is enough.
And from V we can get W.
Yes.
And PQ is also a prime.
PQ, we take the closure of PQ. So PQ, R, S, T, U. Then from R, we are getting U, V, and from V, we are getting W. Okay, so PQ is the candidate key here, right? PQ, R, S, T, U, V, W, R, S, T, U, V, W, PQ, yes.
Sir, the proper subset of candidate key means what, sir? It should be a prime attribute or
Proper subset of candidate key.
and
If A, B, C is the candidate key, then proper subset will be A or AB or BC or B. These are all are the subset of CK, right?
yes, sir.
Yeah. So in this case, PQ is the yes, PQ is the candidate key. Okay. So is there any partial dependency here?
Yes, sir. First and second one is second and third one.
Second and third. Okay. P proper subset, yes, and R is non-prime attribute.
Sir, sorry for interrupt. Sir, PQB is the candidate key.
But from R we are getting the UV, no? And from V we are getting the W.
Okay, sorry, sir.
So this is violating our second NF condition, right? It is a partial dependency. So it is not in 2NF. So highest normal form will be 1NF only, right? The simple one. Okay. Okay, so how many of you solved this question? Question number 5 based on MVD.
Sir, actually, I didn't get any option.
Any option means here.
Yeah, I couldn't get any answer for this.
Did you try this example?
Yes, sir, I have tried it.
Okay, tell me, what is your approach?
Yes, sir. First, I went through the options, sir. Over here, course name is in LHS, so I started from that basic things and the tuple T1, T2, T3, and T4. I went through it.
T4, right? So what is the condition for what is MVD? T1 alpha equals to T2 alpha. No, if okay, 1 minute here. Yes. What is the condition for MVD?
So T1, T2, T3 and T4 should be equal in alpha, and T3 and T1 should be equal in beta.
Yeah. So at the before that also there is one line, right? If there exists T1 and T2, like T1 alpha equals to T2 alpha, then there exists T3 and T4 such that there are 4 conditions, right?
Yes, sir. That
So
is what.
T1 alpha equals to T2 alpha equals to T3 alpha equals to T4 alpha.
Yes.
Then another condition,
T3 beta
T3 beta
equal to
equals to
T1 beta.
T1 beta.
Yes, sir.
And T2 beta equals to
T4.
T4 beta.
Yes, sir.
And both one
T1 R minus beta.
beta equals to T4
T4 R
minus beta. You need to remember this, okay?
1 4 becomes 2 3.
Yeah, T3 R minus
Beta.
Beta equals to T2 R minus beta. These are the conditions for. Okay, so let us apply. Okay, first condition satisfied. T3 beta is instructor here. So T3 T1 T1 Gita, okay. T2 T4, okay. R minus beta. R means course name, instructor, book, edition, and beta here is instructor. So R minus beta will be course name, book, and edition. Okay.
Yes, sir.
So T1 should be equals to T4. 1, 2, 3, 4. right? So it is not satisfying our this condition. So now let us change the tuple. This is T4 and this is T3. T3, right? No. Okay. This is T1. Then 3, 2, 2. Okay. So this will be T2, T3, and T4. Is it visible? Wait, I will write it again. You understand why I'm changing this tuple? Because it is not satisfying, right? It is not
Yes, sir.
following.
Then it won't satisfy the, if you change the tuples, it won't satisfy the second and third condition, no, sir. That T3 beta equal to T1 beta and
You
T2 beta.
consider this T2 and T3, and this one is T4. Then.
Now here T1 beta is not equal to T3 beta.
T1 beta is not equal to T3.
Beta is instructor.
Yeah. Okay, wait. Beta. So we'll consider this T3. This is
T4.
Wait.
That can be T4, na sir.
This can be T4 and this can be T2. Let us check. R minus beta is okay. T2 equals to T4 beta. Okay, this one is correct. Then T1 R minus beta. So R minus beta T1 is DBMS beginner 3 and T4 is DBMS beginner 3. Yes. And here R minus beta is DBMS expert and T2 is DBMS expert. Yeah. So T1, T4, T3. If we consider this T1, T4, T3, and T2, then our condition is satisfying. So then we can say that we need to check for other options also, okay? Because for Java also this condition is satisfying. So similar concept you can apply for this thing also, right? So from here you can say that course name determine multi-determine instructor. Now you need to check for each and every functional dependent.
Sir, my doubt is that now as option 1 is correct, can we tell option D is correct?
If you apply that infer to the Armstrong axioms rule, then you can say that, right? Say this is alpha, this is beta. Okay, so which one are X union Y? So alpha, beta union, course name, instructor. If we minus this course name and instructor, then we are getting book and edition. Yes. If we apply that rule, so we are getting course name multi-determined book edition. Are you getting it what I have done?
Yes, sir. Then now D is also correct.
Yeah, D is also correct.
Sir, then one more thing. If RHS has two attributes, then how to check the multi-valued thing?
If there are two attributes.
In the RHS.
RHS. Okay, here.
Like option D. Over here we could apply the axioms, but if we are not able to do that, then how will check?
Consider this as alpha and this as beta total. And apply the same condition here.
Okay, sir. Okay.
First condition is here satisfied. Now T1 R minus beta is, so beta is book and addition. So R minus beta will be instructor, right? So T1 instructor equals to, now in this case we need to change the tuples, right? Let us take this T1, T2, T3, T4. Now T1 R minus beta, that is beta. Right. T1, if we consider this, we need to consider this as T1, and beta is T4, and this is T2, and this is T3, right? So beta is book and addition. So if we subtract from R, we are instructor. So T1 instructor equals to T4 instructor, and T2 instructor equals to T3 instructor. Yes. Same condition we can apply here. Okay. Just consider the whole as a beta.
Okay, sir. Okay. Yeah, thank you.
You can check for this two multi-dependency also by applying the same condition. Okay. But the correct option will be here A and D. In graded assignment question, there is one question based on MVD. Okay. So yeah, you can try that question. It is very good question. So if you are able to solve that question, you can solve any question on MVD. Okay, is there any other question that you didn't understand practice assignment? Because many of you have not solved this question. So yeah.
Actually, we'll try it again, sir. Now we got some idea.
So this one is easy.
So sir, we have to keep changing that T1, T2 and all that combination.
See, yeah, once you fix this T1, T2, T4, T3, then you have to check for all the condition. If it is not satisfying, then you can change. Okay, but say suppose if you consider T2, T3, T4 and means for this condition, and for this condition you are changing this sequence, then that is not correct. Okay, first you have to fix the sequence, then you have to apply all this condition.
Yes, sir.
Yeah.
So in this case, let's say we are getting 4 conditions, and there are 4 tuples, and I mean we can change 4 times. So we can do that for 16 times, let's say. But in the second case, there are 1, 2, 3, 4, 5, 6 tuples, and we can arrange them in 4. That means we are getting many. There can be many possibilities. So
yeah, so for that you need to practice such question. Once you practice more question, you will get an idea which tuple we have to consider and at what in which sequence. Okay.
okay, sir.
Just practice 2-3 question. Then after that you will just able to figure it out whether it will follow the MVD or not.
Okay, sir. Okay.
Yeah. Once you have done the practice, it will not take much time.
And I mean, it might take time, but I just asking you as to prepare a strategy. That's why that it is better to write down the table, no sir, in our copy.
Yes, you have to work it this example, right? In the exam also.
Yes.
Directly
Yes.
you cannot conclude.
No, directly. I mean,
It will be very difficult.
check the screen. Yes, sir. That is.
Yeah. So you get the rough sheet in TCS center, right?
Yes, sir. Yes, sir.
Okay. Okay, any other doubt? Okay, we already discussed similar question. This question. Okay. So what we have discussed here, similar concept is applied, but in a different way. You can try out. Okay. Yeah. So any doubt in week 6 content? Anything?
Sir.
Yes.
Sir, in the previous session, sir, I asked a question and in the discourse. So
Yeah. So based on that transitive dependency, right? AC determine E.
yes, yes.
Yes, sir. Actually, we discussed that. So yeah, it is not a transitive dependency, but we are not 100% sure about it. Okay. So we discussed with the other team member also. Just 1 minute.
So AC will AC be a prime attribute or a non-prime attribute?
So which
Even
one?
let's say AC, A is a prime attribute. So AC that will be a that will be a non-prime attribute, right?
So A is a prime attribute and C is a non-prime attribute, right?
But AC what we can
No.
say about AC?
AC is neither a prime attribute nor non-prime attribute.
Oh, okay. That also exists. Okay, okay.
Yeah. So that's why we are not 100% sure on that. We discussed with the other team member also.
Okay, okay, sir.
Yeah. We can say that it is a non-transitive dependency. Okay.
So it will be a non-transitive dependency. That is for sure.
Yes. From where you get that example?
Sir, actually, this relation and this functional dependency was given in one of the activities only. So but this question was not asked based on that activity. So, but while solving, I mean, I somehow thought that I was not able to understand the 3NF condition on that relation. So I asked, sir.
Okay, okay. Just 1 minute. Huh? Oh, yeah, sorry. Yeah. So it is a transitive dependency. Yeah, we can say that.
It is a transitive.
Well, not transitive dependency. Yeah.
It's not a transitive.
It was a very good question actually. Yeah. We discussed with other team member also.
Okay, sir. So it is not a transitive dependency, but here we used to say that when NPA is determining another NPA, then it is a transitive dependency. That rule is not fulfilling.
No, because A is a prime attribute here, right?
Yes.
And C is a non-prime attribute. So we cannot say it is a together it is a non-prime attribute or not.
Okay.
Yeah.
So here we have to check that, literally check whether there is any transitive dependency or not. Okay.
Yeah. Okay, any other question? Anyone? Okay. So very few people have solved the practice assignment question. Okay, no issue. Any other question you want to take in practice assignment? Let me check. Okay, no issue. Okay, so we will take one question. If no one have any doubt, should we do? Concept of MVD is clear, right? Multi-order dependency. Okay, how many of you have watched the lecture 6.5, 6.4 and 6.5? All the videos. Please raise your hand.
Sir, actually, I have a doubt in that.
Yes.
Sir, if we have only the MVDs, is that possible to find the closure for that and using that axioms?
If you have only MVD, right? No
Yes,
functional
sir.
dependency.
Only MVDs. We don't have any functional dependencies. Then is
No,
it
no.
possible?
In that case, it is not possible, right? Because yeah, reverse is not true, right? We discussed one example earlier.
Yeah, sir. Yeah. Okay. Then we can use the axiom of MVDs only when we have that including functional dependency.
Including functional dependency means no. Like you want to use Armstrong axioms, right? For MVD.
Yes, sir.
Yes. So there are different rule for that. Okay. That same functional dependency rule will not applicable here. It is given in the slide. You can check and you can compare those rules. Okay.
Okay, sir. Okay.
Okay, anyone would like to volunteer for practice assignment question? Okay, if it's okay, you have not solved this, but you can try this out. Question number 10. It will take time. Question number 8. It will also easy question. This is okay. Yes, question number 10 we can discuss. Yes, anyone would like to volunteer? How to go about this? We have to check whether the decomposition, when that is PCNF or not. Sorry. Hello, anyone? Yes. Okay. You can try this out. Anjana, do you have slide for MVD?
Yes, sir.
Okay. Can you present that and explain?
Yeah, sure, sir.
Okay, thank you.
It's visible, right?
Yes, visible.
It's visible, right?
Yeah, ma'am. Visible.
Okay, so now let us discuss about multi-value dependency. So, we use multi-valued, like MVDs are basically required when a unique tuple determines multiple different tuples, right? Okay, so it is also like a 4NF is also somewhat dependent on multi-value dependency. So, okay, let us begin. So, as you know that for FD is basically represented by, say for example, X determines Y. So it is FD is basically represented by a single arrow. However, MVD is represented by a double arrow. So it can be like that, or we can also write it in this manner, right? Okay, so now from the definition perspective, say we have a relational schema R, and alpha and beta are subsets of R. So alpha multi-determines beta holds for all pairs for tuples T1 and T2 in R, such that tuple 1 of alpha should be equal to tuple 2 of alpha, which means that if two tuples have the same value, then there exists tuple T3 and T4 in R, such that then there are certain conditions which need to be followed for checking whether MVD exists or not. So let us take an example. Remember one thing, that for checking whether MVD exists or not, as sir mentioned previously, that there should be more than 2 attributes. Also, say for example, if we have alpha, beta, and gamma, then we should make sure that beta and gamma are independent of one another. So let us take alpha, beta, and gamma. So our first condition was that if two tuples have the same value. So let us take in alpha have the so let us take 1 1. Okay, then we will have to follow certain conditions need to be followed. So the first condition is that T1 of alpha should be equal to T2 of alpha, should be equal to T3 of alpha, should be equal to T4 of alpha. So let us take these 4 tuples. Let us write it down as T1, T2, T3, and T4. If this condition satisfies, then what we have to check is that tuple 3 of beta should be equals to tuple 1 of beta. So let us take it as 2 and 2. Okay. Then we will check this condition a little later. Before that, let's head to this condition that says T4 of beta should be equal to T2 of beta. So let us take it as 3, 3. Okay. Then here comes this condition T3 R minus beta. Now what R minus beta means, if you can remember the set difference operation, that minus R minus beta means the attributes that are left except beta. So it will be alpha and gamma, right? So as we have already satisfied the condition where all the values of alpha are equal, right? So now we'll check for gamma. So let us consider R minus beta as gamma. So our condition is T3 gamma should be equal to T2 of gamma. So let's write it down as 4, 4. And our next condition is T4 of gamma should be equal to T1 of gamma. So let us take it as 5 and 5. So if all these conditions are satisfied, then we can say that alpha multi-determines beta. Now let me explain it in a simpler manner. For checking whether MVD exists or not, we must at first check whether in alpha there are two tuples having the same value or not. If there are two tuples having the same value, then there must exist two more rows having the same value. Okay, so that way we the first condition satisfies. After that, the next condition is that if the value of T3 in beta is equal to the value of T1 in beta, and the value of T4 in beta is equal to value of tuple 2 in beta, then our final condition is that tuple 3 in gamma. What is gamma? Gamma is the attribute that is left, right? Tuple 3 in gamma should be equal to tuple 2 in gamma, and tuple 4 in gamma is equal to tuple 1 in gamma. So if all these three conditions satisfies, then we can say that MVD exists. Okay, now let us try to understand it with the help of an example. So here, instead of alpha, beta, gamma, we are simply taking course name, instructor, book, right? So here we have to identify whether course name multi-determines instructor or not. So let us take course name as alpha, instructor as beta, course name as alpha, instructor as beta, and we can take book as gamma, right? Okay, so if you can recall, our first condition was to check whether two tuples of alpha are same or not, right? So here we can see, let us take it as T1 and consider it as T2. So as we can see, Java, so yes, this condition satisfies. Then we'll head to the condition that says T1 of alpha equal to T2 of alpha equals to T3 of alpha equals to T4 of alpha. So now let us check whether this condition satisfies or not. So we'll take these two tuples as T3 and T4. Right, now let's check Java. So yes, this condition satisfies. Then our next condition was T3 of beta should be equal to T1 of beta, and T4 of beta should be equal to T2 of beta. Now let us check whether these conditions satisfy or not. So this is tuple 3 and this is tuple 1. So Rahul, yes, it satisfies. Then tuple 4 is equal to tuple 2. Yes, these condition also satisfy. Then our last condition was tuple 3 of gamma should be equal to tuple 2 of gamma, and tuple 4 of gamma should be equal to tuple 1 of gamma. Now let us check whether this condition satisfies or these conditions satisfy or not. So tuple 3 tuple is equal to tuple 2, Java intermediate, and then this condition satisfies. Then tuple 4 Java export is equal to Java export. So yes, this condition also satisfies. So by that we can say that since all the conditions are satisfied, so we can say that course name multi-determines instructor. Okay.
One question here.
Yeah.
The order of tuple is important here, or
No. Yeah, you'll understand this in the next example, in this example, okay? So that was your question, right? The order of tuple. I'll just explain it to you. Say, so here we have the same table. Just we will consider, instead of instructor, we'll consider book as beta, alpha, and we'll consider instructor as gamma. Okay. So see, from the previous example, we know that the first condition satisfies, right? So we'll directly head to the next condition, that is T3 of beta equals to T1 of beta and T4 of beta equals to T2 of beta. Now let's check whether this satisfies or not. So this is T3 of beta and this is T1 of beta. Java Intermediate, Java Expert. So as we can see that this condition does not satisfy. So here what we can do is we can change the order, or we can change this, we can change the order of tuples. However, you should it is not mandatory that the order of tuples should be in sequence, like T1, T2, T3, T4. It is not mandatory. However, one thing that you should always remember is that the order should remain the same throughout all the conditions. What I mean by that is that, say for example, for satisfying the first condition, you are simply taking, I'm just giving an example, okay? So for satisfying the first condition, we are considering T1, T3, T4, and T2. Then for considering the next condition, like for satisfying the next condition, we are taking it as T1, T2, T3, T4. So that won't work. Remember that. The order should remain the same throughout. Whoever asked that question, you understood it, right? I can.
We can only change the order once to satisfy our condition.
Exactly, in the beginning.
In the beginning. After that, we cannot change the order.
No, after that we have to consider that order only.
To check the value of gamma.
Exactly, gamma, beta, alpha, everything.
Everything. Okay.
Yes.
Thank you.
Okay, so since we had this 3 and 4 and it was not satisfying the condition, so let us try and change the order. So let me take this as 4 and this is 3. Now let us check. So this is T3 and this is T1. So as we can see, yes, this is satisfying. Then the next is T4, tuple 4 should be equal to tuple 2. So yes, this is also satisfying. Then our last condition was T3 of gamma should be equal to T2 of gamma and T4 of gamma should be equals to T1 of gamma. Now let's check whether these conditions satisfy or not. So T3 equals to T2 Arman and T4 equals to T1. So yes, both these conditions satisfies. So by that we can say that course name multi-determines book. Any questions, any doubts?
Excuse me, ma'am.
Yeah.
If there are more than 4 rows, then how to do the calculation?
Like if we have one more, right? Like Java.
I mean, 2 more rows. Let us better even number. 2 more rows.
Okay, so Java, same, right?
Java only.
Okay, and the instructor name? Okay, so what you mean is that we have 6 same column, same rows, right? Hello?
I mean, now the new instructor for these 2. Like, let us keep your name only, ma'am.
Okay. Okay, so we will keep it as Anjana and then?
Down also Anjana.
Okay.
Now this say Java Expert 1 and Java Intermediate 1.
1.
Expert.
1? Or just expert?
Expert.
Okay. And then
down one Java Intermediate.
Okay. Okay. So look, what happens is we have to follow the conditions, right? In the conditions, we are given 4 tuples, right? We are given 4 rows. So in the condition, like, just a minute, like here, if you can see that there are 4 tuples, right? If T1 equals to T2, then there exists T3 and T4, right? So we must consider the 4 tuples. If there are 5 or 6 tuples, like a more 1 or 2 tuples as we have here, then if like since okay, these tuples follow these rows, these 4 tuples follow the satisfies the conditions, right? As we have just proved right now, these tuples satisfy the condition. So if there are any more number of the same tuple, it does not really matter, because we have already proved that this particular 4 tuples satisfies the condition.
So the other rows can be any value. I mean, if at least 4 rows satisfy this condition, then we can call it a MPD.
Yes.
So
Yes.
the other rows doesn't matter. If we can find at least 4 rows that are satisfying these 5 conditions, that's enough.
Yes. From my knowledge, that is it. But Piyush sir, would you want to add something if I'm wrong?
Like we previously have done one question. There are 6 rows of Java.
Yeah.
That so
You have to take. You can take different combinations of T1, T2, T4, T3. Okay, if it is satisfying that condition, then we can say it is an MVD. But yeah, so the like other attribute must be the same. Like it should have the all the 4 attribute on the left hand side should be same. Java. If it is there one more attribute, say DBMS on the left hand side, then you cannot compare that DBMS with the Java.
yes, sir.
So you
Yes,
got it,
understood.
right?
Thank you.
It depends on the data set.
Am I audible?
Yes, Anjana. Yeah.
Then the conclusion is if there are more than 4 tuples and the course name is same in this case, then we can say the multi-valued dependency is there, right?
In this case, it is there multi-row dependency.
Yeah, because the first 4 one satisfy.
Yeah, in the row we have added Anjana, and then Java expert, Java intermediate. Right. So if you can consider this the T3 and T4, then it will still satisfy the condition. But if you consider Java, Anjana, and say DBMS expert, then in that case, how will you identify that? If you consider that tuple as a T3 or T4, anything. Okay, so have you watched the lecture 6.4? In that, sir has mentioned about the crossing of the tuples. Like there is one slide in which sir has explained that concept. If you apply that concept here, then you will be able to answer that.
Okay, sir.
Yeah.
Okay.
And one more thing, ma'am. If there are more than 3 attributes, then R minus beta will be the rest of the attributes, right?
R minus beta. Yes, correct. If there are, say, for example, course name, instructor, book, and we have another
Index
attribute.
right? Like
Sorry?
index and like index, yeah, or anything else.
Yeah.
Then,
say we have another attribute that is a course ID. Just taking an example, okay? Or say we have department. Say we have another attribute as department. So what we can consider here is instructor and department will be gamma. Both instructor and department must follow these 2 conditions.
Now, if you consider course name multi-determined book, that multi dependency hold to, in that case, that instructor and department should follow,
Yes,
right?
correct. In this
For the
case.
particular MVD, yeah.
thank you.
Okay. Any more doubts? Okay. So then, if you can recall, we had some Armstrong's axiom or inference rules in FD. Similarly, we have some inference rules in MVD as well. There are in MVD we have 3 rules which only relates to MVD, and then there are some rules like 2 rules which relates to both MVD and FDs. So so we'll begin with the ones which involves MVD. So the first one is complementation. So here, if X multi-determines Y, then X multi-determines R minus X union Y. Now, you might be getting confused what is R minus X union Y. So say for example, in the previous example, we took alpha, beta and gamma, right? So let us consider X, Y as alpha, beta, okay? So say alpha multi-determines beta, then alpha multi-determines R minus alpha union beta. Now, what the value of R minus alpha union beta is, if you can remember from set difference, it is alpha union beta minus R. So it will be the attribute that is left in R except alpha and beta. So that would be gamma, right? So ultimately what it basically means is, if alpha multi-determines beta, then alpha multi-determines gamma. Okay. Then there is this another rule, that is augmentation. We also had augmentation and functional dependency. In FD, we had it like, if X determines Y, then say AX determines AY. However, in FD, the attributes that are added on both the sides should be same. Here in MVD, if X multi-determines Y, then Z is a subset of W and Z is a subset of W, then WX multi-determines YZ. Okay. So here both the attributes can be different, just that the attribute on the right hand side should be a subset of the attribute on the left hand side, the attributes which are appended. Okay, then our last rule is transitivity. So if X multi-determines Y and Y multi-determines Z, then X multi-determines Z minus Y. That is the attributes that are there in Z and the attributes that are there in Y. The attributes that are there in Y will be deducted, and only the attributes that are present in Z will be there. Now, these are the rules which basically involved MVDs. Now we will head to the rules which involves both FDs as well as MVDs. So our first rule is replication. Here, if X determines Y, then X multi-determines Y, but the reverse is not true. What this basically means is that all functional dependencies are multi-value dependencies. However, the reverse is not true, right? Then our last rule is coalescence, that is that states, if X multi-determines Y and there is a W such that W intersection Y equals to 5, which means that there are no common attributes between W and Y, and W determines Z and Z is a subset of Y, then X determines Z. So these are some of the inference rule. Now we also have trivial multi-value dependency. Like in FD, for a functional dependency to be trivial, in FD, for a functional dependency to be trivial, if X determines Y and Y is a subset of X, then we can say that X determines Y is trivial functional dependency, right? This was the rule for checking whether trivial FD exists or not. However, here in multi-value dependency, to check whether a trivial MVD exists or not, the same condition is also applied here. But there is also another condition, like say for example, if Y is, by chance, if Y is not a subset of X, then there is another condition, that is X union Y should consist all the attributes that are present in the relation. So either of these two conditions should be there for a MVD to be trivial, to be called a trivial MVD. right? Okay, so these were the rules. Now we'll discuss this example where more than 3 attributes are present and we have a set of attributes to multi-determine. So let us take it as beta, instructor and course as beta, and SID as alpha. So SID as alpha, course and instructor as beta, and the leftover attributes we can simply consider it as gamma. Okay, so our first attribute, would anybody like to volunteer, like procedure, via following the procedure? Would anybody like to like volunteer what we would be checking first, what conditions? Anyone? I'm audible, right?
Yes, ma'am.
So would anybody want to volunteer, like what we should check first and what we should be doing?
First, we will take T1 of alpha equal to T2 of alpha is true or not. I mean, we'll check it. Then we'll extend it to T3 of alpha and T4 of alpha.
Exactly. So here it follows, it's this condition satisfies.
Yes, ma'am.
Okay. Okay. Then what was our next condition?
T1 of beta equal to T3 of beta.
Yes. Okay. And for beta, there was another condition. Can you recall?
T2 of beta equal to T4 of beta.
Okay. So can you tell whether this particular condition satisfies here or not? So here, let's say T1 of beta equals to T3 of beta. This satisfies in course attribute. Let's check an instructor. So T1 of instructor and T3 of instructor does not match. So now what we can do is we can again try and change the order and check whether it satisfies or not. So let us take it as T4 and T3. I'm just taking it randomly. Okay, so let's check now. So this is T1, this is T3. So in course only, it is not satisfying these conditions. So if it is not satisfying one condition, is there any profit of going further? There is no advantage, right? Because one of the conditions is not satisfying. Okay, let us check for T2 equal to T4. T2 equals to T4. Yeah, again, this is also not satisfying, right? So certain, yeah.
Ma'am, in this condition,
Yeah.
the instructor and course are not functional dependency. So from that condition, we can also say that it is not MBD. Because Java and instructor, they are not functionally defining the same thing.
Hello. Yes. Actually, we are taking the combine of attributes like Toja and course and instructor. So Java and S George and Java and MK Singhania. Right. So instructor determine course. Okay, it is not valid here, but we are taking that as a combined attribute like
Yes,
course and
Java
instructor.
and Judge, and if there is Java and Judge, then only we can check whether it is in T1 or T3 or T5. We can check, and DBMS and the instructor name and any other tuple with DBMS with same name. Then only this condition is satisfied because the course and instructor are not functionally dependent. So it will never gives us the second condition to be true at any condition.
Yes, yes. T2 beta will not be equal to T3 beta, right? T4 beta, yeah. DBMS and also function dependency, yeah.
Because in our special cases, if it is functional dependency, then it will multi-value.
Right, right.
So this is not functional dependency. So we do not need to go further. If I am not wrong that much.
Yeah, from that we can tell it is not an MVD. But if you say it course determine instructor. Right, yeah. We can infer that from this. Yes, Savit.
Whether my approach is correct?
Yeah, means for this particular question, we can say that. But what if we add more records, say DBMS and S George, and then institute number be different?
Okay. Anjana ma'am, can you change it this table? Then we can go further.
Like you want me to change how the value?
Java and the S George name changed to MK Singania, and
Singania.
DBMS we can add S George. Then we can go further.
Java and S George's DBMs, right? Like this, right?
Correct, ma'am.
No. For this condition, it will satisfy, no?
Yeah. Then we can go further.
Yeah. Now it is in MVD, right?
Sir,
Yeah. Now it is following the condition.
Maybe or may not be. We have to check. That third
we have to
condition
check,
is gamma is also there.
Yeah, so gamma is also there. Yeah. Okay, so Anjana, first you can. Okay, so did you explain this SID determine instructor course?
Yes, sir.
Okay, now you can take this. Okay, DBMS Java. Now we can check. Okay, apply the same condition. It will not be an MVD. Yeah.
Okay, so the first condition is T1 equals to T3. T1 equals to T3, T1 equals to T3. Yeah. So this satisfies. Then the next one is T2 equals to T4. So yes, this also satisfies. Then our next last condition is T3 of gamma should be equals to T2 of gamma, and T4 of gamma should be equals to T1 of gamma. So let's see. Here in S name all the attributes are, all the values are same, right? So if we check for T3 equals to T2, it is same. T4 equals to T1, it's also same. Now let's check for nth row. So T3 equals to T2. No, it is not satisfying. So no, sir, it won't work. And T4 equals to T1 is also not satisfying. I'm audible, right? Hello?
Yes, ma'am, you are audible.
Yeah, so it's not satisfying.
Yes, it is not in MVD. Yeah.
Okay, no issues. Okay, so we have this another example here. This is the same table, just we are taking instructor and instrum as beta. Okay, and these two will consider as gamma. Okay, so from the previous example, if we can recall that it follows the first condition, right? So T1, T2, T3, and T4. Our next condition was T3 of beta should be equals to T1 of beta, and T4 of beta should be equals to T2 of beta. Now let's check whether this satisfies or not. So T3 of beta equals to T1. No, it is not satisfying. So now let us check by simply changing the order of the tuple. So let me take it as 4 and 3. Now let's check. So T3 equals to T1. Yes, it satisfies. T4 equals to T2. Yeah, oh sorry. Yeah, in both it is satisfying. So this condition satisfies. So we'll head to our last condition, that is T4 of gamma was equal to T1 of gamma, and T3 of gamma should be equal to T2 of gamma. So now let's check. So since S name has all the same values, so we don't need to check for S name. Now let's check for course. So T4 equals to T1, yes, it satisfies, and T3 equals to T2. Yes, it also satisfies. So by that, we can say that SID multi determines instructor and instrum. I hope that is clear to you. Any doubt? Any questions? Anyone?
No question, ma'am, but I have observed one thing, that if beta is more than one attribute, then both the attributes are functionally dependent from both the sides, right? Means instructor depends means instructor determines instrum and instrum determines instructor. Can we say that?
Yeah, you can say that. Yeah. Yeah, you can somewhat say that because 201 is having S George and S George is having 201.
Only then the attributes can be in beta or in the gamma also.
Yeah. We don't need to, I think I guess we can simply like check the conditions. We don't need to think about the functional dependencies and all. But yeah, your observation is also correct.
Okay.
Yeah. Anyone else? Any questions? Any doubts? Any doubts? Anyone?
Okay. Any question? Okay, so please solve the practice assignment question. Okay. Okay. Any doubt in practice or activity question? So today we discuss, I think 3 questions from practice assignment question. So you can solve the rest of the question. Okay. Please try that question. And question number 10 in practice assignment question. Try to solve in a detailed way. Means don't go through the options. Try to decompose that relation into BCNF. Okay. Then check whether it is correct or not. We can discuss that question in the next session. Okay.
Which questions?
Question number 10, practice assignment.
Okay.
Yeah. Try to decompose that relation R into BCNF. Okay. Don't solve by looking at the options. We'll discuss that in the next session. Yeah.
Okay.
Okay. Any other question? Any other doubt? Okay. I guess we can wind up then. Okay. Thank you, everyone. Yeah.
Thank you all.
Yeah. So please solve practice assignment question. Okay. We'll discuss that in the next session. Yeah. Okay. Thank you then. Yeah.
Hello.
Yes, Abhishek.
Can we ask doubt from week 5 as well?
Okay, just a second. Yeah.
Okay.
Hello.
Yeah.
Yes, Abhishek.
So I have one doubt in activity question of week 5. That is AQ 5.5 question number. That is the last question of
AQ 5.5 last question.
Yeah.
Okay. Okay. Just 1 minute. I'm sharing my screen. Okay, so did you try this question? Oh no. Actually, I left the meet, so I'm not able to share the screen. Anjana or Pradeep, can you share that question? I'm not the co-host now, I think. Hello, Anjana, Pradeep.
Yes, sir, just a second.
Yeah, okay. You joined now, Abhishek?
Yes, sir.
Yes, sir. What is the question?
The last question.
All right.
So what is the condition for lossless decomposition? What are the conditions?
So condition is that R1 intersection R2 should be empty, should not be empty,
Should not be empty, okay.
and their intersection may either provide R1 or they can provide R2, and that is I think not a necessary condition. And third one is there's one more condition.
All the three
R1
conditions are necessary, okay.
Okay.
So first
So
one
R1
is, yes, sorry, yeah. Go ahead.
R1 union R2 should give R. That is
R.
Yeah.
So it is satisfying first condition, right? A, B, C, D, R1 union R2.
Yeah.
Yeah. So next condition is R1 intersection R2.
Yeah.
So the common attribute is B. Right?
Yeah.
So what is the functional dependency so that I can get either R1 or R2 minimum? If I add B determine D, then I will get the R2, right?
Sorry, sir. Can you come again?
Okay, so intersection is B, right? For R1 and R2.
Yeah.
So either B should determine R1 or R2, then we can say that it is a lossless decomposition.
Yeah.
Yeah. So for that, what is the minimum number of function dependency we require? Say we have B as a common attribute. So B either should determine R2 or R1. What is the minimum number of function dependency?
So that means B should be the primary key of this particular relation.
Yeah. So B, if we add B determine D for R2, then it can determine R2, right? So
Yeah.
it will become lossless decomposition.
Okay.
Minimum number is 1, right?
Yeah.
Yeah. So either way, you can write it as B determine AC also. From that, we can get R1. So minimum number is function dependency required is 1 only, right?
Yeah. Sir, what about the question number 2 in this particular activity only?
Okay, can you scroll? Okay. Yeah, same concept is applied here. So first we check for R1 union R2 union R3. It is giving the relation R or not?
Yeah, it is giving.
Yeah. Now consider any two relations which is having common attribute.
Yeah, B is the common. In R1 and R3, we have common attribute B.
Okay. So from B, can we determine R1 or R3?
Yeah, we can.
Yeah. So we can take that two decomposed relation. So R1 intersection R3 is B, and from B we can determine R1, right?
Okay.
Now let us say R12 equals to R1 union R3. Then R12 will become A, B, D, E, right?
Right.
Now take R12 and R2. What is the intersection between those two? They will common attribute
E.
E. Now from E, can we determine R2 or R12?
From E, we can determine, yeah, we can.
Yeah, from E, we will get BD, right?
Yeah.
And from B, we will get A. So we will get R12.
Can you say it again?
Okay, so R12 is R1 union R3, right?
Yeah.
Sorry, R13 is R1 union R3. So that is A, B, E, D, right?
Yeah.
Now we have to check for R13 intersection R2. Now in that common attribute is E, right?
E.
From E, we can determine either R2 or R13.
Yeah.
Yeah, so we can determine R13, right? A, B, E, D from E.
Yeah.
So this decomposition is a lossless decomposition. So none of the above will be the answer.
Okay. And one more question doubt I have in this. So question number 4 also.
Same activity. Okay.
So in the lecture, sir has basically equal to relation. If the decomposition give me is equal to the all the unions,
Mm-hmm.
sorry, to all the joins, natural joins, then it should be
Lossless.
lossless. But here the correct answer is the
Did you read the question? Choose the incorrect statements.
okay.
You have to select the incorrect statements.
Okay, that's what.
Yeah.
Okay, let me check. And sir, this question, like this is maybe yeah, question number 5th also. So both
Question number 5.
yeah.
Yes.
So a lossless decomposition. Sir, what is the meaning of dependency preservation basically?
Yes. Anya, can you scroll down? Yeah. Who is Pradeep, right? Yeah, so when we
See,
decompose one in a particular relation R into say R1 and R2, then that parent functional dependency is valid or not if we decompose the relation R1 and R2.
Okay, that is dependency preservation.
Yeah.
sir,
So
may
many
I add
of
something?
yes, yes, Subhendu, yeah.
See, dependency preserving means suppose a parent table are decomposed into R1 and R2 child table. So parent table dependency are preserved in the child table or not. This is called a dependency preserving.
So if we have, let's say A determines B and
Yeah.
B determines C and then C determines D.
Yes.
So if we have, so we can say A also determining D, right?
Uh, eh, yeah. Yes.
So it is not mandatory that directly in parent relation that this particular relation should hold in the parent relation.
See, those dependency are present in its parent table dependency. Those dependency are present in or not. So you have to see only those dependencies.
Okay. And what about the second statement, sir?
A decomposition that preserve dependency ensure that its join will be lossless. See, lossless lossless join and decomposition preservation both are different things. So we cannot compare we cannot conclude that a decomposition that preserve dependency always be lossless. So both
Okay.
are these are the
3
second
NF,
one is
yeah, up to 3 NF decomposition, we can say that okay, the decomposition is lossless and dependency preserving. But directly we cannot conclude if it is lossless and then it's dependency preservation also, right? So
Okay.
both the statements are wrong here.
Okay.
Yeah.
And sir, I have seen one question there in this particular week. So is it mandatory if a form is in BCNF, then it should also be in 3NF?
Yeah, if it is in BCNF, then it is in 3NF, 2NF, and 1NF.
So BCNF is fourth normalization or second normalization?
BCNF is a different form of a third normal form. Okay.
Okay.
4NF is different concept. In 4NF, we do not have any multi-order dependencies, so that we have discussed today.
Okay.
Yeah.
Okay, that's all my doubt. Thank you.
Okay. Yeah. Okay. Thank you then. Yeah. Any other doubt? Anyone? Still 32 people are here. Okay. Okay. Thank you then. Yeah. Yes, Nihil. Yeah. Snehil.
Yes, sir. Am I audible?
Yes. Can you speak louder? Yeah.
Hello.
Hello. Yes. Yeah.
Yeah. So I had a doubt that if I find a closure of an attribute,
Okay.
for example, let's say a closure is covers all the attributes, right? So A should be the primary key.
If it covers all the attribute in the present in the relation R, then it should be a key, a candidate key.
A candidate key.
Hmm.
If A alone covers all the attributes, all other attributes, then it's a candidate key.
Yeah, it is a candidate key.
Okay, and if we choose it, then it becomes a primary key.
Yeah. If there's
So
only yeah.
So all attributes that are a single value, that as in if suppose B also covers all other attributes, then B is also a candidate key.
Yes, B is A and B both are the candidate key, but any of them is a primary key. Okay. So table can have only one primary key, but it can have multiple candidate key.
Okay, and what if A and C cover the entire thing too? Or let's
A and
suppose
C.
C and D. Let's suppose C and D attribute together cover all the other attributes. So is C and D another candidate key?
Yes, CD is also another candidate key.
Because it's still not minimal, because the minimal
Yes.
is A and B.
It's still candidate key. If you take the combination of A and B or CD, as you said, with any other attribute, then it will become super key, right? So
okay, so any attribute added to independent
candidate key will become a super key.
Okay, sir. Thank you. That's what I was confused about.
Okay.
Yeah, sir, may I add?
Yes, Pradeep.
Yeah, you can see there is a C and D is a candidate key.
Yeah.
Okay. Yeah. Any proper subset of C and D should not be candidate key, means super key.
That is minimal set, yeah.
That is minimal. So if there is C is a candidate key, suppose you find out that CD is a candidate key.
Yes, sir.
And C derives all the determines all the attribute uniquely, right?
Yes, sir.
Yeah, C or D is, then CD is a not candidate key. Then you can say CD is a super key, C and D is the candidate key, right?
Yes, sir. So if I have to find the number of super keys of a given relationship, I should just find the candidate keys and add all other attributes to it, right?
Yeah.
Yeah, you can take the combination, right? With
combination of all other keys with it. Okay. Thank you, sir.
Yes. Thank you.
Any other question? Okay, thank you then. Yeah.